Okay, thanks to all for joining us in this research engagement meeting, the first research engagement meeting hosted by the Sim Center this semester. The topic of this meeting is going to be on global sensitivity analysis applications to natural hazards engineering. We have, 6 excellent speakers. I'll start with an overview, then Sangri, we're going to discuss estimation of global sensitivity using the Sim Center tools and also quickly go over the educational module that we have available. And then we have 4 speakers that are going to specifically discuss 4 different GSA applications. So Gaofeng, Jersina, Bunhee, and Puria. For the participants that want to interact during the presentations, you can pose your questions with a Q&A button. Also, after the end of all presentations, we expect that's going to take us around 50 minutes. We'll open to open-ended discussion, and if you want to pose a questions at that point in time verbally, you just can simply raise your hands. Otherwise, I will be discussing some of the panel will be discussing some of the questions that all of you have posed. Okay, so I'll start with my part of the talk. This is going to be the setup. It's a presentation that I jointly developed with Sangri. So my name is Alexandros Taflanidis. I'm a professor at the University of Notre Dame. Sangri is an assistant professor at Rice University, and she was previously a developer for a lot of the Sim Center tools related to UQ. So this is going to be an overview of global sensitivity analysis, and I will discuss this from the perspective that some of you might not have heard at all what GSA is. So let's try to motivate the problem. Okay, so we have a simulation model that has an n-dimensional input vector, 1 up to xn, and we have a scalar output y. And this input vector takes values. It's not deterministic. It takes values within some domain of possible values. This could be for a variety of reasons. Maybe it's a random variable. Maybe it's a design variable, or maybe it's a parameter that we try to calibrate. In the next few slides, I'm going to provide specific examples of these 3 cases. So again, vector, that takes values within some range of possible parameter values. The question that we're asking is, what's the global importance of the different components of X? Is X3 more important than the X1? And while we're interested in that questions, ultimately we try to figure out, are any components exist that we need to emphasize or some other that we can completely ignore? In order to better frame this question, let's look at a couple of examples of these 3 cases here. So I'm going to start with probabilistic modeling. I'm going to be using, my model now is going to be a truss bridge. Y is going to be the displacement, for example, in the middle of the truss. And that the X in this case is going to be my random variables. It could be material properties, size of elements, loads that are uncertain. I have some probability distribution, and ultimately I'm estimating the probability that the displacement is going to exceed some threshold, the failure probability, for example. Now, I might not try to understand what components of X drive the probabilistic performance. Is the material properties as equal of importance of the size of the elements? Is something more important than the others? I might try to improve modeling. For example, I'm interested in getting more information to change these probability distributions. Are some components that I should focus on? Do spending more effort to better understand the material properties is as beneficial? In other words, it changes as much the probability of failure as spending effort to better understand what are the loads are. But also I could be interested in purely improving the statistical accuracy of my estimates. So in generally, when you apply a lot of adaptive Monte Carlo techniques, we know that you get more substantial benefits if the adaptive implementation focuses on some key components instead of the whole vector. So in that case, we'll be interested to understand, hey, what are the components that we should focus on to get this better improvement in computational efficiency? So that's a probabilistic modeling example. Now we're going to convert it to system identification. In this case, I measure the loads, I measure the displacements, and I'm trying to infer some material property size of elements. You can be doing this with the least squares, based on updating, it really doesn't matter. This is a problem where sometimes you have an identifiability where your information is not enough to identify all the parameters. So you might be asking the questions, can I remove some parameters because really they're not critical? But more importantly, you might ask the questions, hey, can I improve computational efficiency without really sacrificing the quality of my calibration if I don't try to identify all parameters, but I focus on some of them? And lastly, third example, optimization. Again, same breeds. In this case, I'm trying to optimize this X is the size of the elements. So I have some objective function that's a function of the response, and I'm trying to figure out what is the optimal size of each of the elements. Again, the argument here is computational efficiency. If X is a high-dimensional vector, we know that your optimization algorithm is going to take longer to converge. So the question is, without really sacrificing the quality of the optimal solution, still getting the same optimal solution, can I focus on some of those components and ignoring some others that really don't have any impact on the behavior of the objective function? So that is the question that we try to explore. And now let's look at what global sensitivity means. To do that, I'm going to start with the counterpart that we all are semi-well aware of, local sensitivity. Like local sensitivity, in reality, you will investigate it using gradients. You're going to take the partial derivative with respect to a specific component of your vector xi, and you're going to evaluate this local sensitivity at a specific location. That's why we call it local sensitivity. It looks at this partial derivative of only at a specific value of your input vector. On the other hand, global sensitivity, you try to understand the influence or the sensitivity across the entire range of the values xi, considering all possible values for all other parameters. And here I'm just going to try to demonstrate it with a two-dimensional example. So y, in this case, is a function of both x1 and x2. And here I'm taking the projection of the y with respect to x1 and y over to x2. So you have here variability because the other parameter varies. In this case, for this specific plot, it's going to be this variability comes from the fact that x1 varies. So really, you sort of the simplest way to understand this all possible values of all other parameters, you can sort of be looking at the regression, over this swarm. And the influence across the entire range is like you're looking at how the behavior changes across all possible values of x2 or x1 here. Even from this simple demonstration, I would come and say, yeah, probably x1 is not important because you see like this regression line is flat. And x2 seems to be important. Now, of course, the question is this qualitative, how you can quantify this global sensitivity. Now, there are different versions of global sensitivity. You can base it on entropy. You can base it on a variety of other terms. The most common, and the one that I'm going to focus specifically on this presentation, even though some of our presenters later might have some additional, flavors that are going to come and use, is variance-based global sensitivity analysis or analysis of variance. So how does variance-based global sensitivity works? You're looking at the decomposition of the total variance to the specific components. Now let's pick for the time being one of those components and try to understand it. So and I'm going to denote as xi that component that I'm interested, as x not I the remaining ones. So this VI term here is the variance of the conditional expectation. So you are considering the conditional expectation with respect to this expectation with respect to the all other components. So it would be, in this case, it would be, hey, this green line here, what I was calling regression before, and the variance is going to be the variability along this green line. So this is sort of you can think of it to some extent as the equivalent of a Taylor series expansion of a function. So this is sort of the expansion of the variability with respect to the individual components. But of course, you need to consider the higher order. So these terms here looks at the interactions between pair of components, and then you need to consider per combination of three components and so forth. Like this will be the higher order. Now, another way to consider this decomposition, if this is a little bit confusing, is to come and use the total variance theorem. For total variance theorem, we know that the total variance is the variance of the conditional expectation plus the expectation of the conditional variance. We know this is an exact identity. This is the part of the variance that's explained by xi, and this is the variance that's explained by remaining components. So this sort of blue term would be this variability that's created by the swarm. So, but most commonly, if you look at the original, Sobol's work, it's this decomposition that is used to come and provide this definition of Sobol indices. So Sobol indices are just going to be each of those components divided by the total variance, and this Sobol indices shows the global sensitivity with respect to the component that you're looking at. So we have the definition of the first order index. It is each of this VI divided by the total variance. So really what this first order index gives you, it is the importance of xi excluding any interaction with respect to all the other components, okay? So it's just looking at purely how does xi influence your output y. Then you have the second order interaction indices. These indices look just the importance of purely of the interactions between xi and xm. As you can see here, you come and subtract the individual indices. So this is sort of the joint interaction of xi and xm as a group, but here you subtract the individual indices to just come and look at purely, hey, how does the interaction, what's the importance of the interaction? Beyond that, you can have the total effect indices. So the total effect indices are a little bit weirder than rather than being the variance of the conditional expectation, the expectation of the conditional variance. In no reality, this is why we call them total effects. Their importance, there's still the importance of xi, but includes all the interactions. So the first order index is just the importance of xi excluding the interactions. This is the importance of xi including all the interactions. Generally, the total effect index is the components of all these possible summations that include I. So it is not just xi on its own, but it's all the other possible interactions that can be attributed to xi. So these are the key indices. Now, of course, you can also define the first group index. It's going to be coming and looking just on this term here. So it comes and looks at the importance of xi and xm as a group, including the interactions, but also their individual contributions. Now, each of those indices gives answer to a different question. For example, the first order index is going to tell you what is the relative importance of each individual components on their own. The total effect index is going to provide answer to the questions: what is the importance of individual parameters when you include the interactions with other parameters? Or perhaps it gives the answer to the question: what parameters are important and can be ignored? Having a small first order index, it doesn't mean necessarily you can ignore that parameter, because there is a likelihood that that parameter interacts significantly with other parameters. Having a small total effect index means that, yeah, you can ignore that parameter. The second order, the interaction indices, gives information about what's the importance of the interactions, and the first order group index, it gives, it answers exactly this question, but when you look at, in this case, I and M as a group. The most commonly used indices, also the easiest to calculate for a variety of reasons, are the first order and total effect index. And the one most commonly used is the first order index. Sometimes the first order index is used even in lieu of the total effect index, because total effect index is hard to calculate. These are really some quick examples that go back. You can look at later the details of each of these papers. This is going to be for example, probabilistic modeling, basis of the structure under near fault excitations. You can do this estimate analysis. I'm going to come and tell you, yeah, the near fault pulse really dominates the reliability estimation. This paper came and looked at the system identification problem. It started with potentially 15 parameters and they realized based on sensitivity index, yeah, a bunch of them can be ignored. Some parameters would say way easier, calibration problem. This is a multi-objective optimization problem of a pipe network. By doing some sensitivity analysis, you realize these are the important pipes. So rather than solving the full problem and have a slower conversion, I can just try to calibrate these pipes, and I will much faster converge to exactly the same solution, but I'm going to do it with lower computational effort. So those are the gains that you can get. So especially if you have not seen global sensitivity analysis before, you would maybe ask yourself, hey, this is a really great tool. Why have I not heard of it before? Or why have I not used it before? Well, the answer is these indices are really hard to estimate. So especially if you come look at the naive approach, double loop estimation. Monte Carlo estimation, this is a double loop. It has two statistics, a conditional expectation and then a variance. So, and this estimation will be different for each index. So very hard to estimate. Now, luckily, there are some alternatives. Those alternatives still require some computational effort, but they're way more efficient. So you can do smart sample techniques. You can use surrogate-aided approaches, either to accelerate the estimation or to leverage the surrogate model statistical properties, or you can use sample-based approaches from auxiliary densities. Especially this second, family of approaches are really attractive because you can easily integrate them within existing frameworks. In other words, you don't really need to focus on the GSA estimation. You can just leverage these approaches as a supplement to whatever you were doing to additionally come and give you the GSA results. And a couple of final slides. Now, so far I was looking at, scalars, what happens when you have a high dimensional output. Well, in that case, the sensitivity will be different for each of your outputs. But you might be also interested to do an aggregated sensitivity across the outputs. One of our presentations later will touch on this point here exactly. And really to accelerate, the computations for this high dimensional output, you can use some dimensionality reduction rather than, especially if M is really large, rather try to estimate the global sensitivity for each of them. You project into some latent space, and then you do the computation of that latent space to get computational efficiency. And this is especially true if you're doing analysis of variance, because a lot of the properties under linear transformation, especially if your dimensionality reduction is something like a PCA, they really translate well. And the final slide, what happens if you have transform inputs or outputs? So for example, many times when we do probabilistic analysis, we like to transform to a standard Gaussian space, or we might have some transformation of the output. For example, this could be EDP, this could be log EDP. What happens? The sensitivity indices are invariant under any invertible transformation. So for example, the sensitivity indices are for Z1 is going to be here exactly the same. For Z10 is going to be exactly the same. These correlated variables that map jointly to these correlated variables, the joint sensitivity is going to be the same. Now, the individual, though, they might be different, because in this case, you don't have a one-to-one mapping between Z2 and X2. And for the transformation of the output, now, on the other hand, that's going to change your sensitivity. So sensitivity with respect to Y or some function of G of Y, those are going to be different results. So that is the overview. We're going to shift now to Sangri. That's going to pick from where I left off, and it's going to provide a little bit more details on the computational estimation. Sangri, you can share and take the lead.
Thank you, Alex. Can you everyone see the screen? Yes. Okay. So I will talk about global sensitivity analysis modules inside QuaFM. So QualFam is one of the software tools we developed in SimCenter. And the idea is that it's uncertainty quantification enabling tool. So user brings the model and we provide probabilistic analysis algorithms. And among the algorithms, sensitivity analysis has been one of the most popular methods that users like to use because it's very useful. Our algorithms are pretty robust. And it also can run using existing data. So you don't need to provide the model, but if you do provide model, you can use our design save resources to accelerate the things. So as you just heard, the key of understanding computing global sensitivity analysis is to first identify the mean trend of output versus the input of your interest, and then to collect the level of variation you observe in the this mean trend prediction. So there are two algorithms that will enable us to do this inside QualFam. First is called Smart Monte Carlo method or smart sampling. We call it smart because we want to strategically generate samples instead of randomly generated. But still, this is Monte Carlo method, so it's very stable. It doesn't have any model assumptions, and so it converges to the true value as you have enough number of samples. However, to make sure the sample is located at the place that we want, we ask user to provide the model so that QualFam can have control over the sampling. But other cases, you may have only the data, like only input and output data and not the model. So in that case, you can choose our other algorithm, which is data-driven, fully data-driven. We call it probabilistic model-based algorithm. So in this case, we base on existing random samples, and we feed a parametric model to understand this mean trend. So this one is data-driven, meaning you can provide only the data set, and it's efficient. If your model is expensive, so you cannot create lots of samples, then this parametric model can help us fill in the gap in the number of data. So using only maybe a couple of hundred of samples, you can still get pretty accurate result that can be practically useful. So let me go into more detail on this algorithm and also show you how this algorithm is extended to more advanced approaches. So in this algorithm, we start by either randomly generating samples or ask users to import data sets if they already exist. And then we fit the samples into this two-dimensional model, output of interest and input of interest. For this, there can be different parametric models, but we adopt the approach from this paper, which uses Gaussian mixture model to fit these data points in two-dimensional space. And then once this parametric model is fitted, identifying the mean trend is trivial. It's closed form expression using these parameters. And once we know the mean trend, we can easily translate this into Sobol indices. So this approach has been excellent. It's efficient and flexible. And also the way it works allows us to extend this approach to estimate group Sobol indices without running any additional simulations. So by group Sobol index, we mean that we want to evaluate collective impacts of input variables. For example, consider you have a structural model and you want to understand the influence of these parameters to the structural response. You can run sensitivity analysis for each of these parameters, but if you want to overview this system in a more aggregated view, then you may want to categorize these parameters into several groups and then obtain sensitivity indices for each of these group of parameters. To obtain this, it's pretty straightforward extension. So now when you're evaluating this mean trend, you don't just want to get it in this one input variable domain, but you want to have it in multiple input variable space that covers all your parameters inside the group. So in this case, the mean trend will be something like surface instead of just line. And your parametric model should be able to help you understand this mean trend. And for this, it was straightforward to apply high-dimensional Gaussian mixture model to fit in this high-dimensional space instead of just two-dimensional space. So this example is actually one of our recent work. So we repeated this exact group sensitivity analysis for different level of ground motion intensities so that we can understand how these parameter contributions will gonna change as we increase the intensity of our ground motion. And to achieve this, a straightforward way of achieving this kind of curve could be that we repeat this sensitivity analysis at different levels of ground motion intensities. But that can be pretty computationally expensive. And we encounter this kind of situation very frequently in engineering applications. For example, you may want to understand the contribution of your parameters to entire time history outputs, not only like a single point, but entire time history, or your modal output may be some spatial field. So in that case, we are having high dimensional outputs. So to accelerate sensitivity analysis for such situations, what we have implemented is to introduce dimension reduction module to deal with this high dimensional output, for example, using principal component analysis. And then what we do is to run sensitivity analysis for this latent variable, and then we can unfold this latent variable sensitivity into our original high dimension of sensitivity variables or sensitivity fields. And this is allowed because of this PCA's linear transformation properties. So the exact algorithm we adopted comes from this paper, and we were able to verify our algorithm by reproducing their storm surge example, which you will gonna learn in more detail in the later presentation today. But this example is pretty intense because it has 2 million outputs. It has 500 samples to learn sensitivity. And we were able to run it using within 5 minutes on a personal computer. So we have very efficient handling of these high output matrices. And just to show you a brief idea on how straightforward it is to run sensitivity using our tools, I wanted to show you that using this button, you can select one of the two algorithms I just mentioned. And if you select probabilistic model-based algorithm, you can either choose to import data points or import simulation model. So if you import data points, it's really just formatting your data into some standard format and importing, specifying their path through our user interface. But if you choose to import a simulation model, you can also do it through the button here called FEM. We call it FEM, but it's really any kind of simulation model. So you just need to change their interface to fit in one of our standard SimCenter model interfaces. And then there are these advanced options to specify whether you want to run global sensitivity, global Sobol analysis, or to make your high dimensional output efficiently processed internally inside QualFEM. So all of these method algorithms and references are written in our documentation. And if you need to troubleshoot, we have an active user forum at GitHub. And we really want to say that we think this global sensitivity analysis is very useful and practically useful in many applications. And also, I think this is a great skill set for students to learn, and they can learn it within a small amount of time with really focused effort. And to facilitate this, we have prepared course modules that can fit into regular classroom environment. It's just like a couple of weeks of course materials prepared for you. So if you are interested in teaching sensitivity analysis in your classes, or if you're just interested in learning more about this topic, please find SimCenter website publicly available. So with that, the end presentation.
Of GSA or different approaches and the tools that are available for the SimCenter to estimate GSA. Now we're going to shift a little bit the discussion. We're going to look at for different applications of in terms of hazard, in terms of system models, of how sensitivity analysis has been useful. So we're going to start with Gaofeng. So Gaofeng, you can share your screen and the floor is yours. So that the presenters know, I think I'm going to follow the list that I originally have in my first slide, which is Gaofeng, Jersina, Wunhee, and then Puria at the end. Gaofeng, remember to unmute also.
Just 1 second, let me share this. Okay, can you see my screen?
You're good to go.
Okay. First, thanks, Alex, for the invitation and this opportunity to share some of the work related to GSA. And also I see Sanri presented the tool, which looked very nice, and also especially the educational materials look very interesting. Definitely I'll look into that. So today, for me, I'll share some of our recent work using GSA mainly for tsunami evacuation risk assessment and mitigation, how we used GSA. And before I start, I'd like to say that this work is mainly by my former PhD student, Dr. Zhenqiang Wang, who is currently a postdoc at Oregon State University. So the area we're studying we studied is the seaside in Oregon, and we studied this one because the location is subject to the Cascadia subduction zone, which could trigger big earthquake and could cause subsequent tsunami, and also this particular town is highly vulnerable to tsunami inundation because of the relative flat topography, and there are some rivers, and also the transportation network has some, this yellow highlighted one, some bridges, right, crossing some rivers could be potential bottlenecks in terms of evacuation. And the overall evacuation is also very complex here because it's tourist town and depends on the time of the year. There may be big variation in terms of population. For example, summer there could be twice of the population in winter, right? So it's a very highly susceptible to this tsunami risk, tsunami inundation risk. So that's why sort of we started this area. And to really do this, we have to build a model to simulate everything. And in this case, we use the agent-based tsunami evacuation model. So in this case, we need to model the entire community, including the transportation network, all the roads and bridges, and also the different evacuation modes, because people may evacuate on foot or they may choose to evacuate by car. So here you see each of these sort of orange dots represent either a person or a car, right? So they will be evacuating on this transportation network up to these tsunami shelters here, these boxes. So for the evacuation, we can model this, but one thing to pay attention is, or we need to include, is that the multi-hazard, right? So besides the tsunami inundation, prior to that, the earthquake already happened, which most likely, right, could have done some damage to your infrastructures, the buildings, the roads, the bridges, right? So when we talk about evacuation, it's not evacuating on an intact, transportation, is evacuating on this damaged network, right? So we also need to model that. And here it's basically this video here just shows one of the runs that we have. You see people start evacuating to these shelters, and then around half an hour later, the tsunami wave arrives, and if people cannot escape that, then it may become casualty. So again, this is a brief overview of the model that we used. And as you can see, there's so many components, right? So there's the hazard, there's the damage, there's the network, and more complex is the people's behavior. When do they decide to evacuate? How do they decide to evacuate? There are a lot of variabilities in this. So here, like, as I said, there are so many uncertainties related to the damage, maybe the population size or distribution where they are, right? And whether they decide to use car to evacuate, or whether they decide to just follow others, or they follow the some of the evacuation routes, right? So there are so many variabilities in this model. So that's why to really understand this, we need to propagate these uncertainties. And here is written as this integral, this capital H, is the tsunami evacuation risk that we're interested in, and depends on the output of the model, which were in lowercase hx, right? So x is input, hx is output, and here is just some risk performance measure, for example, related to casualty, if you're interested in casualty, or it could be something related to time, if you're interested to be how much time people have to evacuate, right? And we know that for these different uncertainty, we can represent it with random variables, and here as expected, different inputs may have different impacts on the evacuation risk that we are interested in, right? So here, what we're interested in is if we can identify those that having higher or larger contribution, so-called critical risk factors, then we can use this information to guide either our modeling, or more importantly, guide the selection of some of the risk mitigation strategy, right? How can we reduce risk? And here, the approach we use is, right, so using the probability sensitivity analysis, right, trying to figure out out of all these variables, which ones has higher contribution to the evacuation risk. And here, earlier Alex mentioned a little bit, right? So most common one, people use the Sobol index, but earlier, we also look at using relative entropy to quantify this global sensitivity as another measure, right? So it's just a different measure, you can think of it that way. So here, just very briefly, I'll just explain it a little bit. So here, if you recall this, our evacuation risk integral has its integration with h x px, right? So here we just define this auxiliary distribution that is proportional to the risk integral. And here, our sensitivity is quantified by comparing the distribution, this distribution pi of x, and the prior distribution p of x. And of course, this is for all the variables, but a lot of them are interested in individual variables or group of variables. In that case, we just need to look at the corresponding marginal distribution, or compare the marginal distribution of these two distributions, pi and b. And the larger discrepancy indicates greater sensitivity. And to really, how do you quantitatively, describe this or characterize this is using the relative entropy, right? This is for the continuous, and this is for if the random variable is a discrete variable, which we have, right? Later on, we'll talk about that. And as mentioned, Alex also mentioned, to calculate this is, if you just directly calculate it, you see here, there are some high dimensional integrals that you need to repeat, so which is not feasible for a lot of the cases. So basically here we use, or we developed this sample-based approach that is much more efficient. And in this case, we generate some samples from the distributions and then use KDE to estimate these distributions instead of the red one carrying out this multi-dimensional integral. We can just once we have the samples, we can efficiently evaluate the sensitivity for all the variables or group of variables that they're interested in. So that's a very brief overview of what measure that we use, which is the relative entropy. But if you're interested, you can look more into this. But just a note here that you may be wondering, okay, how does this relate to the Sobol index, right? Actually, they are related. And we have shown that, if you look at the Sobol index, the first order index, and it can be actually expressed in terms of these two distributions that I mentioned, the pi x and px, right? So it can be, so in other words, they are related. You can think of they're just different measures, right? Different measures of the sensitivity. Okay, so that's the sensitivity that the measure that we use with relative entropy. And so next we'll show a little bit some results. So here, these are some results, right? So we show the relative entropy values, and these are some of the parameters. I will not go into details. Based on the sensitivity, we find that actually the proportion of people evacuating by car or on foot has a very big impact, mainly because of, if a lot of people evacuate by car, then you have this congestion issue. You end up being, taking more time than evacuating on foot. So this is the PC, we call it, this has the most important impact. Then there are some others, and I want to highlight that these are the related to damaged states. So the bridges, remember earlier I talked about, there are some bridges that could be bottlenecks in the evacuation. So our sensitivity analysis also, confirmed that these are the top 5 bridges that you see have big impact. And overall, in terms of the ranking of some of the parameters, the proportional evacuees using car and the damaged states of the bridges, and also the percentage of people using the evacuation routes. And this one looks a little bit more in detail. So here, actually, we look at the entire transportation network, look at each segment, what's the sensitivity, right? So each road segment, and also these are the bridges pointed out, right? So we're able to do this, because the approach allows us to, right, easily look at this very efficiently, because in this case, we do have super high dimensional random variables. And finally, right, so how can we use that information? We identify those are the critical risk factors, right? Then accordingly, we can target those when we design the mitigation strategy, right? So we find that the proportion of evacuees taking cars is important. How can I address this, right? So you can widen some of the routes so that it's less congested, or you can build some vertical shelters so that people don't have to go very far always to the shelters. They can have some shelters nearby. And also in terms of non-infrastructure mitigation strategy, you can do these evacuation drills and also educate people so that they take the proper evacuation mode, let's say. And also, the bridge is important. What you can do is you can retrofit the bridges so that it can reduce the evacuation risk. And also, this is proportional people using evacuation routes, right? So how can you encourage that? So you can do this preparedness education so that to encourage people using some of those routes. Again, I'm not going to detail. These are just some results showing some of the effectiveness, how before mitigation and after mitigation, if you adopt some of the mitigation strategies, how much you get the risk gets reduced. So I think I'll stop here. I went through things very fast. So if you
Thanks,
have any
Gal.
questions, let me know.
We're drifting a little bit on time, so I would encourage anyone that has questions to pose them on the Q&A. And I will also encourage our speakers to go and look at those questions that pertain to them in case they want to respond. Jasenna, you are next, so you can start sharing your screen and unmute, and the floor is yours.
Hello, everyone. I will present my recent work on seismic fragility and global sensitivity analysis of buried operating steel pipelines. In this presentation, we will first see the methodology adopted to evaluate the response of buried operating pipelines under longitudinal permanent ground deformation. Then we will discuss the obtained deterministic analysis results for evaluating the pipeline performance, followed by the uncertainty analysis, including the seismic fragility and global sensitivity analysis, highlighting the main factors influencing the seismic performance of buried operating pipelines, considering the system uncertainties. The new analytical model allows to evaluate the performance of buried pipelines under longitudinal permanent ground deformation, considering the asymmetric nonlinear stress-strain relationship for the pipe material in tension and compression under varying operational loads. The ground deformation is idealized as a rigid block movement that is defined by a downslope movement delta over block length LB that results in tension crack of width delta at the upslope end and a compression ridge over a distance delta on the downslope end. The magnitude of the total pipeline displacement in tension and compression are equal to the ground displacement delta until the soil friction mobilizes over the entire soil block in case 2, remaining constant thereafter, that is case 1. This allows to directly assess the amount of ground displacement delta that induces a maximum pipeline strain, either in tension or compression, at the soil block head and toe, respectively. This model employs the theory of plasticity for modeling the pipeline material based on the associated flow rule with the von Mises-Yield criterion and isotropic strain hardening. Compared to the state-of-the-art analytical models, the proposed analytical solution accounts for the initial axial thermal strains and biaxial stress state in the pipe due to internal pressure. Critical soil length associated with full mobilization of the soil reaction in case 1 for a given value of soil displacement delta is directly proportional to the overall pipeline load at the edges of the permanent ground deformation zone. Consequently, a certain limit state is reached only if the permanent ground deformation demand exceeds the critical values corresponding to a certain performance criteria. In this figure, we see the variation of the critical soil block length as a function of the ground displacement delta, indicating the critical values associated with the achievement of the performance limit state in the pressurized or unpressurized pipeline. Clearly, the pipeline response depends on the operating loads, with the performance limit states in compression being reached for lower values of critical soil displacements and length in the pressurized pipeline compared to the unpressurized one. To quantify the effect of system uncertainties on the pipeline performance, we have implemented a robust fragility analysis framework based on Monte Carlo simulation, considering the probabilistic characteristics of the input parameters. The limit state functions for normal operability and pressure integrity in tension and compression are expressed in terms of the system demand and capacity corresponding to each performance criteria. The probability of exceeding the normal operability and the pressure integrity limit state, conditioned to the permanent ground deformation intensity measure level, is given by the joint union of the associated damage states in tension and compression. The probability of exceedance of the pipeline performance criteria increases for larger soil displacements and lengths, being greater for the normal operability compared to the pressure integrity limit state. The isoprobability lines are defined by two half lines parallel to the delta and LB axis. This is consistent with the pipeline deformation response observed for the deterministic analysis. Specifically, the median values of soil displacement corresponding to 50% probability of reaching the normal operability and pressure integrity limit state are 18 centimeters and 67 centimeters respectively. Comparison between deterministic and fragility analysis results show that neglecting the variability of the system parameters, including the operational loads, may result in under-designed pipelines, highlighting the importance of uncertainty analysis for a reliable infrastructure design. The adopted global sensitivity analysis procedure is based on the Sobol's variance decomposition method, in which the total variance of the model output is decomposed into component variances resulting from individual parameters and their interactions. The Sobol indices of the random input variables corresponding to each level of permanent ground deformation demand are evaluated using the quantified uncertainty with optimization for finite element method, QFM. The obtained output results are combined through variance-based weighting, giving the aggregated sensitivity indexes. The soil friction reaction per unit pipe length results the most influential parameter, with a first-order aggregated sensitivity index of 56 and 78% for the normal operability and pressure integrity limit states, respectively, and a total sensitivity index greater than 87 for both performance limit states. The pipeline operating temperature results the second most influential parameter for the normal operability limit state, with a first-order aggregated sensitivity index and a total order aggregated sensitivity index of 8 and 37% respectively. While the first-order sensitivity index for the internal pressure are negligible, the total aggregated sensitivity index reaches 16% and 40% for the normal operability and pressure integrity limit state respectively, that highlights the considerable interaction effects of the internal pressure with the other input variables. According to the fragility analysis results, the probability of the pipeline reaching the performance limit states increases for larger soil displacements and lengths because of the greater mobilized soil reaction counteracting pipeline deformation. According to the global sensitivity analysis, the soil friction reaction resulted the most influential parameter on the exceedance of both performance criteria, given that the intensity of the soil pipeline interaction directly controls the pipeline deformation demand. The significant total aggregated sensitivity indexes of the operational loads and pipe yield strength demonstrated the importance of their interaction effects with the other input variables, requiring proper consideration in pipeline system modeling and design. Thank you for your attention.
And Gunhi, the floor is
Yes.
yours.
Okay, so can you see my screen well? Yes, great. Okay. So, yeah, my name is Sung-hee Jung. So, in addition to GSA applications discussed earlier, I'd like to introduce how GSA can also be applied and leverage it for real-time probabilistic storm surge hazard prediction problem. So first of all, let's start with a brief introduction of real-time storm surge hazard prediction. When a storm is formed, the National Hurricane Center issues storm advisory that provides us with information about the nominal forecast of storm features and their uncertainties. In more detail, the uncertainties are quantified using statistics of historical forecast errors for these four storm features: size, cross-track, along-track, and intensity, and their probability models. By generating variabilities in these storm features And combining them with the nominal forecast of these features, we can create storm scenarios. Then a numerical storm simulation can be performed using numerically very expensive but very accurate numerical model for each storm scenario. Aggregating all these storm simulation results, we can finally obtain surge statistics of interest, which represent the storm surge hazard. This is the current workflow of NOAA and can be summarized with this simple Monte Carlo estimation equation. The one thing I would like to highlight at this point is that this storm surge hazard prediction pertains to a large number of locations and each representing a different quantity of interest. So for this workflow, what GSA can do for us are these three big things, but since these are already covered by the previous presentations, I will skip this. What I would like to highlight here is that for this workflow, which is already computationally intensive, we want a efficient GSA approach that can be seamlessly integrated into this existing workflow with minimal computational costs. In other words, we want to leverage readily available and storm simulation results that were used for hazard estimation to perform this GSA. Additionally, as I briefly mentioned, a computationally efficient GSA tool is necessary to accommodate this very high dimensional QI. So these were the motivations for developing the computationally efficient GSA framework in this paper. And as Sang-mi presented, this tool is already integrated into SimCenter tools, so you can implement this framework whenever you want for engineering applications that include computationally very expensive numerical model with high dimensional output, like the one I'm introducing in this presentation. So from now on, I'd like to share some global sensitivity results. So in this slide, I will show some estimated first order and total effect Sobol indices for advisory 20 of Hurricane Sandy. So in this big figure, and I should have noted that I would like to show you the individual sensitivity results for each QI or each location of interest. So in this big figure, in the first row, I'm showing you the first order Sobol indices, and in the second row, I'm showing you the total effect Sobol indices. And each column shows the corresponding Sobol indices for each storm features. As you can see, cross-track seems to be the most important feature for predicting the storm surge hazard in this case. And the difference between the first order and total effect indices suggests that there might be some interactions between these storm features. And as Sang-mi mentioned, as Dr. T and Sang-mi mentioned before, so our efficient GSA framework has a capability of estimating these higher order Sobol indices for some interactions of the inputs or storm features in this case very efficiently. And as you can see, there are some interactions between some storm features, but their values are lower than corresponding first or total effect Sobol indices. And beyond the individual indices, we can aggregate these individual Sobol indices into a single importance index through a weighted average. In this case, we can use surge variance as the weight to obtain this aggregated importance across the all QIs or across the domain of interest in this case. And all the details about this aggregation, you can find the details in this paper. So I've very quickly shown you some GSA results for the real-time probabilistic storm surge hazard prediction, but now I would like to briefly share how these results can be leveraged in this workflow to especially accelerate this workflow. The objective is to reduce the variance of this MC estimation. Among various approaches, I chose importance sampling and multifidelity Monte Carlo for achieving this variance reduction. In this presentation, I will focus only on the importance sampling. The idea is to develop importance sampling density to generate storm feature variabilities for creating storm scenarios, and use and search simulation results from the previous storm advisory to develop this importance sampling density. All the details about this development can be found in this paper. So in the development, since we have limited information, to use the information efficiently, we can prioritize some storm features when developing the importance sampling density. And we can use the aggregate importance indices in some slides ago for this prioritization. For further efficiency, we can also consider marginal or joint formulations in the importance sampling density development. And finally, this graph shows how much variance can be reduced by using developed importance sampling density. So focusing on this part only, so including all 4 storm features achieve the largest variance reduction, but even using a few most important features for development, the importance sampling density, this can lead to decent amount of variance reduction. So this is all my presentations. And
thanks, Munhi.
Maybe.
Appreciate you being on time. So Puria, you're the last but definitely not the least for bringing us home. You can start sharing your slides and unmuting to start the presentation. I will encourage people to keep posing questions on the Q&A. Puria, the floor is yours.
Can you see my screen now? Okay, so yeah, thank you everyone. So my talk is going to be the focus on impact of parameter selection on seismic loss and recovery time estimate. So this work was done in collaboration with my PhD supervisor at the time, Professor Carlos Molinahat at UBC, and also Adam Jarnotchai from SimCenter. So essentially, the main motivation here was just to dive deeper in performance-based earthquake engineering assessments and basically question some of the assumptions that go into these models. So there are so many, of course, there are uncertainties captured at different layers, but there are also so many parameters without even knowing many details are considered as deterministic and constant. So we just want to know if what are the impact of uncertainty and also on the output metrics. And based on the literature, so usually most of the cases when they have done when there has been done research on the sensitivity of loss assessments, they are mainly deterministic and local. And the main focus has been on hazard-related factors. So that's why the main objective here was to perform variance-based sensitivity analysis, which is global, and also look into wide range of different input parameters and focus on the sensitivity of these input parameters and the impact on 2 seismic loss measure and also 2 recovery measures at 4 different hazard levels. So to do that, so basically these analyses were performed at building level assessments and essentially followed the main steps of the performance-based earthquake engineering methodology. And I used SimCenter tool Pelican for that kind of for loss assessment, and also leverage the damage and loss assessment results from Pelican and using the tool that I contributed to the development of that for recovery assessment, which is named as TREDS, Tool for Recovery Estimation and Downtime Simulation, which account for more advanced and detailed repair phasing and sequencing, and also the impact of impeding factor delays on top of the repair time estimates that we get from FEMA P58 type or performance-based earthquake engineering framework. And so I don't need to basically explain because I think the previous talks already highlighted the details about that, but basically I followed variance-based sensitivity analysis and quantified Sobol indices, looked into the first order total effect and also second order Sobol indices to be able to see the interactions also between different input features. So in order to test essentially these methodology and also the procedure, I considered 12 stories. So we consider different archetypes, but for this talk, I'm just going to focus on the results for 12-story modern reinforced concrete shear wall building, which was designed and developed by Marafi et al. And this archetype was subjected to 4 different hazard level, 100 to 2475 year, consistent with 2014 US national seismic hazard models. So we essentially then, of course, there were numerous routes we could go and consider different parameters, but we tried to be selective and focus on different stages of the performance-based earthquake engineering framework and consider different parameters that can contribute to the uncertainty in output and essentially assign truncated normal distribution rather than just a single deterministic value for different parameters at different stages. And the upper band and lower bound for these essentially parameters were obtained based on the literature. For example, if I show you the median of the repair fragility, essentially mainly based on the FEMA P58 assumption is considered at 1%. But however, we assign the essentially range for this parameter, which can essentially play a big role in the probability of irreparable damage in building. And as I mentioned, we considered 2 different loss measures and two different recovery measures. The loss measures were essentially probability of irreparable damage and mean repair cost. And the recovery measures were considered were mean reoccupancy time and mean functional recovery time. And the analysis were performed at 4 different hazard level. And then by doing that, we can get different indices for essentially at different hazard level for all of these outputs of interest. But for the sake of the time, I'm just going to highlight 2 of these essentially output of interest and to show how this could look like, essentially, how this can inform our modeling and analysis assumptions. So for example, in this case, I'm showing the first order Sobol indices for the case of probability of irreparable damage and also functional recovery time. As you can see, this can allow us to better understand if we are, for example, want to do like analysis at low hazard level or high hazard level, what are the key, essentially most important parameters that we can look into. And for example, in the case of functional recovery time, you can see that once we do, like if we have a low hazard level, such as 100-year, damage to elevator or non-structural component can be more critical. As we go higher to higher hazard level, damage to more structural component, and finally the replacement time, which is related to the high probability of irreparable damage in buildings, can govern the essentially uncertainty in govern the variance in the functional recovery estimate. And on top of that, I also basically by quantifying Sobol indices, first order Sobol indices, I realized that essentially in some cases, such as, for example, at the 2475-year hazard level for probability of irreparable damage, the sum of Sobol indices doesn't add up to 1. So basically, then this kind of indicates there might be a potential interaction that can happen at this output of interest. And then essentially what it means that when we want to look into this on a variability in this output of interest, the impact cannot be simply additive. So then there is also complex interaction between different input parameters can happen. And for example, in this case, this could essentially give some key observations that the highest interaction is essentially related to so-called demand-related parameters, which is in this case yield drift ratio and also the modeling uncertainty, which is an additional uncertainty that's added to engineering demand parameters in the context of FEMA P58 assumptions. So this can also allow us to better dive into these assumptions and also the different combination of these two parameters that go into the loss and recovery assessments. And finally, to just conclude my talk and allow more questions. So basically, the main idea here is just to give insights into parameters that warrant greater attention in loss and recovery assessments for buildings, And this can essentially enable in-depth examination of critical assumptions for the most important parameters that can lead to like further refinement of models. If, for example, a risk modeler or an engineer wants to focus on fine-tuning these models and have a better estimates, then this can essentially be guidance to see where the resources and the focus should be targeted to. And also, of course, if I want to highlight the limitations, this was only a subset of input parameters that we decided based on the engineering judgment. Of course, this can be limitless, and we can have so many other different input parameters that can go into these assumptions. And the methodology is generic and also can be expanded to different structural systems and occupancy times. But however, the results I showed here was just reinforced concrete shear wall buildings and also for the residential occupancy type. And also this study, if you want to learn more about that, so here's the QR code. The paper is already published in Earthquake Spectra. And if you want to dive into details, and my email is here, I would be happy to also take any questions here and also after that, if you have any. Thank you. And I would like to then conclude my talk here.
Thanks, Faria. Thanks for keeping us on time as well. I hope that you saw like 4 really different applications, different hazards, different models of how other uncertainty analysis, but more importantly, global sensitivity can give you better intuition, can verify sort of the trends you were expecting to see, but also how you can perhaps use that sensitivity to start exploring different questions or improve your computational efficiency. Before we open the floor to Q&A, I will like to share a couple more slides for those of you that are interested in the broader work of the SIM Center. Okay, so let me come and see. So if you want to be continuously being involved with the SIM Center, you can go to our website and join the community. There are multiple research engagement meetings. They're going to be 3 or more at least. You can use this QR code, or you can directly go to this website to figure out the next research engagement meetings. Those are going to be more focused on specific hazards, and you can join our office hours to talk online with our staff, but more importantly, the next Notre computational symposium co-hosted by the SIM Center Design Safe is going to be held at US Berkeley at May 27th to 29th. The first day, May 27th, is going to be specific workshop on the different tools. So I'm going to stop my sharing, and I'm also going to stop the